Hello there, and welcome to IQT's The Quantum Dragon podcast. My name is Brian Siegelwax, and this podcast has an open architecture. My guest this episode is Matt Rijlaarsdam, CEO and co-founder of QuantWare. Thank you for joining me. Welcome to the show.
Great to be here.
Okay, some in the industry are trying to be the NVIDIA of quantum without necessarily defining what that means. But it caught my eye that QuantWare is trying to be the Intel of quantum. Why Intel?
It's a good question, and I can understand, the marketing motivations to try to be associated with NVIDIA. I think for us, the analogy here is really like looking at this historically, looking at the semiconductor space historically. In the 1950s, everyone was vertically integrated. Everyone made, the whole mainframe computer, like players like IBM, right? Like made the whole mainframe computer, including a customized chip design. And then in the 1970s and beyond, like really the 80s and 90s, they were quite dominant. Intel completely changed the dominant business model by basically creating a pretty standard CPU architecture, which allowed everyone to build and integrate PCs and computers on top of that, which really kicked off these economies of scale and massively lowered prices and made personal computers accessible for everyone. And I think, and actually today, of course, Intel is, has a lot of competition on the foundry side from players like TSMC who have specialized further and have scale and more economies of scale to make, the leading edge nodes chips. And that's, let's say, those laws of economics of specialization, those are exactly the same in quantum. And so what we're saying, by saying we're the Intel of quantum is we are the world's first commercial supplier of quantum processors with the goal of massively lowering, the cost of building quantum computers, which is what we need to do if we want to get to useful economic quantum computers.
Sadly, I'm old enough to remember all that. And I see mass production and custom production. So to show how little I know about chip production, doesn't offering custom foundry and packaging services contradict the mass production angle?
Not really. So way to kind of think about that is the bit that you are then selling is actually like standardized and therefore producible at scale. And then obviously you can make the design of a customer. Roughly, you can equate it to you're printing, the pattern that the customer has supplied, but the rest is all standardized. So there is actually these economies of scale there.
Okay. It looks to me that your chip is two-dimensional and the wires are perpendicular to it, creating a three-dimensional architecture. So first of all, is that correct? And either way, besides using 3D space, how does your architecture affect qubit connectivity, for example? What are the advantages of it?
Right. So I think what you're referring to is what we call VIO, vertical I/O, our scaling architecture. One way to think about VIO, it's a way to take in qubit chiplets, either QuantWare, designed and fabricated, or qubit chiplets from our customer. You mentioned the packaging services. And these chiplets, indeed, like you mentioned, they're integrated in VIO in a way that indeed the signal is brought in from the top, hence vertical I/O. And what that gives our customers or ourselves the ability to design chips where you don't need all this space to route out signal. Basically, 95% of the space today in quantum chips is used to actually route out signal, not to host the qubits. And that's the reason why this industry has been stuck at 100 to 200 qubits for more than a decade. Is that you just simply run out of space if you do need to route out in 2 dimensions. And so VIO brings it from the top. That means that you can make much denser arrays. Like you might have seen VIO 40K on our website. It's 100 times denser than the closest state of the art alternative architectures. Um, and it is much better for performance, things like crosstalk, because those lines don't cross each other anymore. They're actually super well shielded. There's a lot of microwave hygiene.
Speaking of crosstalk, quote, exponentially more compute. Wait, I'm going to get this wrong. Should have had more coffee. Exponentially more compute power per watt and per dollar, unquote, is a bold statement. Is that from eliminating the exponential routing, crosstalk, and yield problems of two-dimensional architectures, or what else substantiates that claim?
So it is a bold statement. It's also 100% correct, and it is actually a really important point to make. Where that originates from is that in these VIO arrays, the connectivity between qubits is either on a chiplet or between two chiplets. And the key feature of a VIO processor is that fidelities between two chiplets are as good as fidelities on a chiplet. In other words, intra-chip fidelity is as good as inter-chip fidelity. And that is an extremely important feature of the architecture, because it means that as you scale up qubit counts, you're not, reducing fidelities between qubits and on a single processor. If you cannot make large arrays out of many chiplets, then the only other way to make connections between qubits that are on different chiplets is either via networking, either via microwave or optical connections, and those have orders of magnitude lower fidelities, and that in turn translates to exponentially lower compute. And we'll publish a paper a little bit later in the year where we actually also show this. Just if you run a logical circuit, the same logical circuit over a VIO architecture versus some architecture where these connections are either lower fidelity or more sparse, that as you increase networkness, that compute power just collapses.
Speaking of density, if we go back 2 questions, you mentioned up to 40,000 input-output lines and up to 10,000 qubits per cryostat. I'm curious, why is that the upper limit, or is that the upper limit?
So it's not the upper limit. We've made a decision here to, like, at QuantWare, what we find really important is, in this space, there's a lot of parties that are making very bold and hyperbolic claims, and we'll have 1 million qubits tomorrow. And that's it's good that we that as an industry we're working on a very big idea, and so it's good that that we have bold statements. But our company is built around actually delivering products to customers, and so VIO 40K will be will ship to customers in 2028. At that time, it will be 100 times larger than anyone else can make in a single array. And so, it's by no means the upper limit. We plan on going quite a bit beyond that. But for cryostats and the rest of the stack that is commercially available. And on that time scale, this is the thing that we're focusing on right now.
For my last question, I'm always thinking about physical footprints and how massive some quantum computers are projected to be. How many server racks of control systems are needed for 10,000 qubits, and how can that number be brought down?
So actually, the space used by control hardware isn't really the issue. You do want to like make those more dense, but I think even at today's sizes, you're probably talking about maybe 10 by 20 meters of surface like this. That's not really the issue. The spacing of it might be a bit more. Um, but to your point about the sizes of these computers, what I do think is important to realize, and what is much more important, and I already alluded to it before, is that we actually bring down costs. And so if you look at a quantum compute stack, right, like we've been public about what the price point of VAL 40K is, which is on the order of 50 million euros. And the response to that has been overwhelmingly positive because 50 million euros is a lot of money, but on a per qubit basis, it's actually 10x reduction from where the industry is today. And that's important to do because if we don't do that and we're going to sizes of 100,000 to a million qubits, then these systems will be prohibitively expensive. And so, and the same holds for control hardware. There's very, but it's really clear on how the industry needs to do this, and it's actually much less a technological problem and much more a economies of scale problem. Going back to why it's important to specialize and get this volume flywheel going. And so, in the case of control hardware, it means that today's these are primarily FPGAs, and it needs to transition to ASICs. And that's a mature technology. You can do an ASIC tape out. It's maybe a bit depending on the node you want to pick, but it's maybe $100 million. And so if you reach a certain volume as an industry, that will just become economical, and that on a per qubit basis will absolutely massively drive down prices. And so you need to look at the entire industry and the entire value chain, and for every bit you need to be able to to project like the thing the industry needs to think about is how we're going to get those cost curves to go down even faster. That is actually the main thing driving useful adoption of this technology.
Yeah, there are actually quantum computers selling for more than that with far fewer qubits. So if the 50 million euros or even not quite 100 million euros, but close to that, there are already quantum computers being sold in that range with less than 2,000 qubits, far less than 2,000 qubits, and one of them is well under 100 qubits. So some
Yeah.
bonus
Yeah,
math
and
there.
so imagine like if that's just linear scaling, imagine that if you want to build a million qubit system, right? Like that would just be 100 billion to $1 trillion. And so if anyone's telling you, well, we're going to build a million qubit quantum computer in a year from now and it's going to be 10 million bucks, that is how cost curves work, right? Like these systems will be large. They and so what you need to do is look at how quickly can we bring down cost, and just from a first principles basis, right? Like what is the material cost, as in the metals and the plastics that go into this thing. So what's like the bottom we can reach if production were 100% efficient, and where's the cost today, and how we're going to bring those together as much as possible. That's really what we need to do.
And with that, I am all out of questions. The floor is yours to say anything else you'd like to say.
Well, first off, thank you very much for having me. I think I like your analogy about why we would position ourselves as Intel, or use that analogy for our company. And I think that's it's exciting to see that also on your podcast, etc. That the quantum open architecture and this idea of, it's not just about doing a cool one-off hero experiment again, but really how we're going to build this industry, get the volumes, and then drive prices down to actually make systems that will impact the lives of, the daily lives of people. It's cool to see that there's space for that on the media in this space. So thank you.
Thank you. Thank you for joining me. And thank you for being my guest on IQT's The Quantum Dragon podcast. Thank you to everyone who's still listening. As always, I invite you to stick around for the outro music. It's called Dungeons and Dragons. Enjoy.